floor is yours.
Thank you. Can everyone hear me okay here? Yeah? Amazing. Take this. Cool. So I'm a PhD student at the University of Bristol, and today I'm going to talk about how we're accelerating greenhouse gas emissions inference. In particular, how we're using graph neural networks to emulate Lagrangian Particle Dispersion Models, and I'll explain what all that means in a minute. But first, we can talk about how we report emissions. Countries report their emissions to the UN yearly using what we call an inventory. That's just another name for a bottom-up estimate. These are just an aggregation of individual sources, so sector data, economic activity, other stats like land use, population. And they're great because it allows you to compare emissions across sectors, across countries. They're very transparent, but they don't actually check this against atmospheric emissions. We don't know if these are accurate. We cannot report what we don't know, what we can't see. So it's really important to validate these against actual atmospheric observations. A way to do this is through what we call inversion algorithms. These inversion algorithms take a prior, so in this case, an inventory that we want to validate, and they check these against atmospheric measurements, often from sites, so big towers with a measurement station on the top. And we can then combine these with the transport model, which simulates how particles move in the atmosphere, to check if our inventories are actually coherent with the emissions that we see. The output of these inversion algorithms are useful to identify hotspots, areas that we're not modeling properly, maybe areas that we're modeling that we're emitting too much and we're not doing that correctly. So they're very good to check these inventories. Currently, only UK, Australia, and Switzerland use these to validate. Why? Because of infrastructure. Only these countries have enough resources to set up the networks that we need to create these atmospheric measurements. The introduction of satellite data to take methane readings is great. It allows us to see, thank you. Does that work? That works? Cool. So satellites allow us to see the emissions of countries that don't have this infrastructure, but that poses computational challenges. So I'll talk about how we can do that in a second. The area that we're working to accelerate right now is the transport model. In particular, I'm working with Lagrangian Particle Dispersion Models. These simulate the dispersion of particles, greenhouse gas particles in the atmosphere. If we run them forward, for example, if we have a source, a methane leak, we can see where these particles would travel to, how the pollution would disperse based on meteorology. Instead, if we do it backwards, we can see for a particular measurement where the air came from, and therefore where it could have picked up the solution. For example, here we have a footprint, which is the output of these backwards running setup. There's a particular measurement here, the blue dot, here in the north of South America, if you can see. That satellite picked up that measurement, and the area in orange is where emissions would have affected my measurement. These footprints, they're very computationally expensive. They take about 10 minutes to be produced. So it's quite hard to produce one of these measurements for all the data points that we have, for all the methane readings that we have. We're working, by the way, with the UK Met's office. We have a model called NAME, which is right there. So why is this a problem? It's because of the availability of data. There's almost too much to process it. The inversion algorithms are defined for sites. They were created for small amounts of data. The UK has 5 sites. That's very achievable to model. When we look at the world networks, we have around 30, 40 sites, still quite doable to process computationally. But when we talk about satellites, it gets out of hand very quickly. GoSat, which was launched in 2009, takes about 10,000 soundings. That's a reading of greenhouse gas per day. Anthropomi in 2017, it's even more, it's 20 million points a day. We just don't have enough computational power to create footprints for each of those measurements. We're missing out on understanding global emissions and validating global emissions, making sure we're reporting these correctly. So this is where machine learning comes in. We can use AI to accelerate this emissions, this footprint production process, and ideally use all of this data. The goal is to get to near real time, so with quite a short period between getting the data and outputting the inference, and ideally on a global scale rather than the regional or national approach that we're doing right now, where only countries with infrastructure and the computational resources can afford to validate their emissions. I'll talk about the machine learning now. Oh, before that, previous approaches all revolve around interpolation, basically running the LPDM, the actual simulation, with only a portion of the footprints and interpolating the rest. This is great. It's very computationally efficient, easy to implement, but it still means we need access to computational resources to get new data. We developed, we published earlier this year, a proof of concept that only uses meteorology. So once it's trained, we don't need any more We don't need any more runs of the actual expensive simulation, which is great because it can run in a normal computer, but it still only works for site data. And as I've said, site data is fine in terms of computational efficiency, and it's satellite where we see more potential to do new countries, new areas that we don't understand well enough. So the goal is to develop an emulator that works for satellite data and that doesn't need new runs. That once trained, it can just work based on meteorology without needing the computational resources to run new simulations. The way we do this is with graph neural networks. Graph neural networks shape the data through nodes. Each of these nodes represents, in our case, a location and has information associated to that location, like meteorology. And we have edges placed between the nodes in where we want to establish relationships, maybe because of distance. These graphs get updated through what we call message passing. In each round of message passing, we update the information in the edges, the nodes, and sometimes a global feature if we need. Missing some stuff over here, fun, but we can imagine what happens. The information in nodes gets updated based on what's happening in the neighbors. So if we do this message passing iteratively, what we get is the distribution of the information across the network. We create an architecture that has a lot of potential in meteorology forecasting. Google published a paper last week that has a lot of potential, which is very exciting. So the way we represent our data is with a latitude-longitude grid. So each of these nodes represents a coordinate with information on that coordinate, meteorology, topography, geographical information. On top of this regular latitude-longitude grid, we have a mesh. This mesh, it's made of nodes in arranged in triangles, because triangles are way more efficient at distributing information than a regular grid. And we put edges between the two to process information, and I'll show that in a second. Another interesting detail is that we center the domain for our inputs and outputs around the measurement point. So for example, if I have, this is a map of the world, we can imagine. If we have a satellite measurement there, the red dot, the green area would be the area that we put our inputs through and that we predict a footprint, so our outputs for. The architecture has 3 stages: an encoder, where the meteorological information gets encoded on this mesh that's way more efficient. In the processor, we do message passing iteratively, so the information gets distributed from one neighbor to the next one, spreads out. And once we've done this as many times as we want, we can then decode the information back to our original resolution and output the footprint value at each of these coordinates. So we have meteorology and geographical data coming in onto the mesh, getting processed, and then decoded back to the value that we want to output, which is the footprint. We demonstrate this with results for GOSAT, so that's the older satellite, and this is only because of data availability, because producing this data for training is really expensive. And we look at Brazil. Brazil is a really big methane emitter, particularly of natural sources of methane, but it's not well understood because they only have one site compared to the network of 5 sites that UK has. So we're looking at this particular case study. We're using as inputs meteorology from the Met Office, wind, temperature, pressure, at different levels of the atmosphere at different times, as well as geographical information. We train for 2014 and 15 with a subset of samples, around 10,000 data points. We validate on the first 3 months of 2016, and we predict the rest of 2016. One of the main advantages of graph neural networks, which is why we chose it as opposed to image-based methods like convolutional networks, is that they're very flexible in terms of domain. So we can train on a domain size of 50 by 50 grid cells, but we can predict on a domain size that's 4 times bigger. This is great for computational resources. It means we need smaller training data. It means we use less training time. And it means that this domain size is relatively arbitrary. We could predict in bigger domains as long as we have the data and the capacity to do so. So we end up predicting in a domain that's around 3,000 by 2,500 kilometers. And now that I've said all this, I'm going to show you some results. Here on the top, we have 4 footprints for 4 locations in South America at different times in 2016. And in the row below, we have the emulated footprints. So the top is the original model output, and the bottom is our emulated footprints for those same times and locations. And what we see is that the model actually captures quite well the spread of particles in the atmosphere. The overall shape is well captured, but it's not doing a great job of capturing the noise in the background. This makes sense. GNNs are not very good at producing noise. They produce very, very smooth outputs. But that's something we're working on, but it's great to see that the overall dispersion is well captured. Another way of evaluating these footprints, because it's really hard to develop metrics to evaluate this, is by looking at the magnitude. So we can take the sum of what's happening here and compare it to the sum of what's happening down there. And compare the time series of the two sums. Here we have the time series of the two sums. In blue, the sums of the true footprints, and in orange, the sums of the emulated footprints. There's quite a nice match between the two. We capture the ups and the downs. But something that we're missing right now is capturing the peaks. If you see that peak is not well captured, that peak at the very end is not captured at all. We see quite a high bias. The model tends to under-predict. Makes sense as well. The data is imbalanced. There's not many of these samples with high sums, but it's something to keep out for because these high pollution events are also very important to emulate properly. But yes, overall, we're doing a pretty good job. This is very exciting. These are the next steps that we need to be able to do this ideally on a global scale and on near real time, so reduce the time between getting the data and producing the emissions estimates. To do this, we need a bigger domain, so we're doing 500 by 100 right now. Ideally, we need to get to 200 by 200. Once this is done, we can do the full emissions, so actually validate Brazil's emissions using these emulation. As I said, it would be great to reduce bias. And something that we're very keen on is on explainability, to make sure that the model actually understands the physics that it's learned, this physics implicitly, although we haven't explicitly told how absorption works. But yes, this is very exciting stuff with state-of-the-art architecture, and I would be very happy to answer any questions if you have any. This is my email.
Thanks a lot, Elena. That's really excellent work. Any questions?
Yeah, I have a question about your next step. So you are going to explain the model. So I'm wondering which approaches you will be considering to explain the graph evidence.
Great question. One of the first ways of doing this is to do really simple examples, so artificial examples. Meteorology is very complex, but we can do artificial meteorology, for example, all the winds going to the east, and see if the model responds in a way that we would expect. There's more complex ways of doing explainability, so for example, altering some of the inputs and seeing if the model responds accordingly, but haven't fully fleshed out that stage yet. But
Another question?
That was great, thank you. And I really appreciate your emphasis as well on the difference in the resources that different kinds of access to. I was wondering, so how are you planning to address that tendency to under-predict, especially with extreme heats?
sure. Oh, sorry, this was a support slide. So one of the better ways would be, right now, we're not filtering the data at all. We're using the data set as is. We could do better class weighting, for example, or create a data set that's a bit more tailored to these peaks. But there's a balance between predicting all the classes correctly versus predicting the more common classes correctly, right? Also, bias correction methods, we're working on those right now, and they actually correct these peaks. Not too bad. So maybe leaving the model as is and applying bias corrections later could be the answer.
Okay, wonderful. Thanks very much, Elaine.